All right, so the problem definitely fits into yesterday. Most students see the inside and the outside, but there's actually something else I want you to see. So depending on if you've started the problem, you might just want to pause and make sure that you too see, oh, well, actually, hold on a second. Maybe what we first want to see here is that this is not the right method. This is Mr. Muck's method. Mr. Muck, he likes to make up calculus, made up calculus. So made up calculus, I suppose here is when someone just kind of charges ahead and says the derivative of x is 1. Now, the derivative of 3x plus 2 to the 6 is the chain rule, which is correct. And you kind of do the chain rule. But the problem here is that this is not correct. Okay, and it's not correct because I want you to see that. Okay, that dot, do you see it? Do you see it? Okay, that dot is the product rule. Okay, now you have to use the product rule to get this problem correct. If you were doing that, good, keep doing it. If you happen to be Mr. or Mrs. Muck, maybe turn around and do a little reset. Good problem to see if you can do that product rule correctly. Looks pretty good. I would expect that you can do the product rule. For most students, it's just realizing when you're kind of out on your own in calculus land that you see the product rule. Just to kind of reiterate, the reason it's the product rule is because there's two functions being multiplied together. One of the functions is x, and one of the functions is this 3x plus 2 to the 6. Both of them have x's. Both of them are functions. So that's always the case when it's the product rule. Again, even if you see a plain old x. Now, if this was a number, then it wouldn't be the product rule. If x was a number, then it would just be a coefficient. And then you could just do the chain rule and bring the coefficient down. All right, so first, derivative of second. Like we kind of saw from Mr. Muck, the derivative of the second is the chain rule. And so you work your way through, you do the outside derivative, change your exponent. Don't forget to multiply by the derivative of the inside. That's the chain rule. So that's first derivative of second. And then we're going to add to that the second, which is actually just recopy the whole 3x plus 2 to the 6 times the derivative of the first. Now the derivative of the first would be the number 1. You don't need to write that, but I'll show it so you guys can see. Okay, so the product rule gets a little big. You also can simplify the coefficients of 6, 3, and the x can come along. So we get an 18x. The rest of it pretty much just gets recopied. You get 18x, 3x plus 2 to the 5th, and then plus 3x plus 2 to the 6th. Okay, I know it sometimes looks easy or not. It's not hard to make mistakes when you're doing it with the teacher, but Love to see people get this right. When you see two guys multiplied together, you got to see the product rule as your roadmap. I saw a couple of you factor out a 3x plus 2. Yeah, you could. You could factor out a 3x plus 2 to the fifth. That would leave behind an 18x. That would leave behind a 3x plus 2 to the first. Nice thing about a 3x plus 2 to the first is that I don't have to put those grouping symbols there, and I can actually get 21x. I am sharing with you that I'm not requiring that, but if you look in the solution manual, you often will see the extra factoring. So sometimes you just need to look back a couple lines and double check your answer. But you can factor it if you want to. It's never bad to practice that. Questions? Anything that you're seeing, how did you get it? I know it's sometimes not easy just to look at math. You kind of need to hear it. Okay, because what I want to do here on day 2 is, as we often do, kind of like advance beyond just what we did yesterday. To be able to advance is sometimes to just understand that there's problems that are going to be a little bit larger, but really they're going to use everything that we did yesterday. I don't know if I want to stand here and say that I'm not showing you anything new, but it is kind of true. We're using what we did yesterday. Sometimes, though, we're kind of combining and creating some problems that are, again, just a little larger. This is one of them. Okay, I don't know if this looks kind of innocent, but it's kind of a beast. We've got sine to the fourth of 2x and the sine of 3x. I don't want to scare you away from trying to do the problem. Actually, what I want you to do is I want you to see something. Okay, when I give you that hint, maybe you're already aware, but I want you to see this product. It's funny, the product rule becomes one of the main rules as we walk through calculus because a lot of things are multiplied together. That's the first thing I want you to see. The other thing I want you to see is how to interpret sine to the fourth. Now, we talked about this yesterday, but it's a good one to see again. Whenever you have a trig function to an exponent, you got to interpret it like the entire trig function on the inside, the exponent on the outside. Now, maybe you don't need to recopy that, but I like to show it that way. I like to show it that way because I hope that that gives you the feeling of the chain rule. Okay, that is definitely the feeling. But listen, it's the product rule that's our roadmap. So yes, I'm going to do the chain rule when I get to this sine to the fourth, but it's the product rule that gets me there. So once again, first would be basically sine to the fourth of 2x. You can write it however you want. Times the derivative of the second. Now, the derivative of the second, maybe this is going to start to become kind of natural for you. But what I'm saying here is that sine is on the outside, so we have to do the derivative of sine to get cosine. Leave the inside alone, and don't forget to do the derivative of the inside. And this is why we call it the chain rule, because you start to chain on these derivatives. So the number 3 is the derivative of the inside. Okay, pretty good problem, but we got to do the other half of the product rule. So now it's second derivative of the first. If you would like to try to do the derivative of the first, if you didn't do it yet, I encourage you to do the derivative of this sine using the chain rule. You want to try to do the derivative of that using the chain rule? We did one like that yesterday. Okay, just kind of do each step at a time. First step is to do the derivative of the outside. Leave the inside alone. Next step is to do the derivative of the inside. Now, the derivative of the inside would be the derivative of sine, which is cosine, but you have to leave 2x alone. And then you do the derivative of the inside, which is really the 2x, and the derivative of 2x is 2. When you are doing a problem like this in your assignment and you're checking your work, now listen, this is how you have to learn math. Like, you do the problem and then you check it, even if you took a picture of it. Okay, I'm not like regulating that because I want you to learn how to manage things and be responsible. So you do the problem and then you go check it. If you see that you're missing something, like you're missing a cosine of 2x, don't just write it down. Go back and figure out why. Okay, if you see that you're missing like a 3, now maybe you'll know why, but make sure that you don't just copy it down. I want you to fix your homework, but I want you to know why you're fixing it. Okay, you should tidy this up a little bit. Like, put the 3 out front. And then as we look over here, you think that there'd be more that you could do, but really the only thing you can do is multiply 4 and 2 to be 8. Nothing else is really like the same. You know, it's the sine of 3x, and then it's the sine of 2x to the third power, so they're different. And then it's the cosine of 2x. So, you know, you'd think maybe something could be put together to become like a combination, like a square or something, but they're not the same. You could factor. I'm going to skip that. But if you look at the left and you look at the right, there are some things that are the same and you could factor them. But not much. And the only thing that you could really factor would be these sines that have exponents. We'll skip that right now. Thoughts. I know I kind of went over the problem, but is there any thoughts on what you see? I think I have this one up on the screen here. Not that, this. I want you to start to become exposed just to some different variables and hopefully not skip a beat. So if I give you an equation that's not really y equals, but I don't know, it's s equals, we can still do the derivative, which is what we're going to do. Now, when you do the derivative, instead of it being dy dx, which means the derivative of y with respect to x, it's going to be ds dt. So ds dt is the derivative of s with respect to t. It just means that t is our independent variable and s is dependent on it. Why don't you think about this derivative for a moment? It's not necessarily the same caliber of the one we just did. You should just be doing the derivative of tangent. Leave the inside alone, and then do the derivative of the inside. Feel free to take a look. So the derivative of tangent is secant squared. Leave the inside alone, and then you do the derivative of 2t, which gives you a 2. Sometimes kids start to do the chain rule naturally. I mean, ultimately, I don't care if it's natural or if you're thinking about it, but it's a chain rule. It's got an inside and outside function. A lot of functions are like that. Okay, so We got a nice little chain rule. Now, the real reason I put this problem up is so we could do one of these guys. Okay, this little phrase, it never really goes away. So if I ask you to find an equation, then we just kind of go to work. We go to work with the slope. Remember, every derivative, when I say derivative, you say slope. Every derivative is a slope. So the formula, 2 secant squared times 2 times t, all I got to do is plug in 2, and you get your slope. Okay? Of course, our ultimate goal is to get the equation, but we need that slope first. You guys might remember trying to do one of these like an exit ticket, basically trying to force you guys to use your calculator correctly. Okay, trying to plug that in the calculator can be a little challenging. I'll give you some suggestion here. Mainly, the suggestion is how to do the secant squared. I'm trying to keep it as simple as possible. Basically, I'm typing in, instead of 1 over cosine, I'm typing in 2 over cosine, just to take care of that right away. So it's 2 over cosine. And then you see where I put the square? I put the square on the outside. And that's the correct way to interpret that. All right, it should be coming out to be, nobody said it had to be something magical. If you get a decimal, I would say you can kind of expect that. So just round it to 2 decimal places, and on you go. On you go to thinking about your y-intercept. Remember, to get the y-intercept, we do need a point. And of course, your point is going to come from plugging in 2, but this time plugging in 2 to that original equation. Okay, so we plug in 2 to the tangent. You can check it out if you want, or just trust me, you get 1/16. All right, it's the same thing we've done a time or two, but I just want you to realize that it works with the chain rule. Okay, of course, when you come up with your equation, you're plugging in to y equals mx plus b, and you're getting that y-intercept. When I did it, I ended up with, negative 8.2. So your equation. Now, I guess we kind of changed the variables up here. We changed them to s and t. I'm not going to care if you guys go back to x and y, if it kind of makes you more comfortable. I suppose technically it should be s and t again. Okay, so we get a little equation. Anything that you guys want to push back on there? What we're going to do is we're going to slide into a problem that is better looked at in your book. I'm going to encourage you to look at a problem on page 148. If you have to take a picture of a book, it's number 57. Okay, it's on page 148, number 57. And then just to kind of gear you up here, probably mainly after lunch, I'll be challenging you with a little bonus problem. It's it's not really an exit ticket, but it's kind of a problem to try at the end of the section, and that'll kind of wrap up this lesson. Okay, but number 57 awaits us. This is usually a crowd pleaser. Usually people kind of remember this kind of problem, and often will ask, are we going to see something like this on a test? Remember that not everything has to be on a test. First off, we just want to try to learn it, but sometimes I'll just grade it on an assignment. Okay, but I'm only sharing those things because I just want you to kind of relax. This is a little bit of a trickier problem, because if you're looking at it, you might realize that it's one of these sort of numeric problems. You're basically trying to do derivatives with numbers. Okay, now I'm not going to do all of these, but I'm trying to pick out a few of them to try to help you guys get a taste of how to do a derivative when you're really just thinking about numbers. I'm going to go ahead and actually skip to letter B. Sometimes I find that students miss the main idea here, which is that you got to do the derivative. So don't just start plugging into f and g cubed. Okay, you're missing the idea. If you look at the directions carefully, it does say that you're supposed to come up with the derivative. Okay, now what that means is we need to think about, how do you do the derivative of f times, that's your answer by the way, f times g cubed. Okay, and did you get that answer? It's the product rule. Okay, we have to do the product rule. Now, doing the product rule with kind of just like numbers and just these functions, well, we got to be careful. So let's be careful. It's first times the derivative of the second. Now, the derivative of the second is like doing the derivative of a chain rule, because you really need to think about g cubed. You have to think about g cubed as g to the third power. You have to think about it as an outside function of 3 and an inside function of g. Okay, so watch, because we're going to do the derivative of the outside, but we're going to leave the inside alone. Okay, obviously that's part of the chain rule, so we do the derivative of the outside, we leave g alone. But you should feel like that you still want to chain on the derivative of the inside. Now the derivative of the inside with symbols would be g prime. And you following that? With symbols, it would be g prime. First derivative of second plus second derivative of the first. Thank goodness the derivative of the first is easier, but when you write f prime, you are doing the derivative. Now you're going to plug in. Okay, you're going to plug in. Now, I'll share with you here that you can copy stuff off the board, or you can kind of like, because I'm going to pause, you can look at your table and just think a little bit, okay, what am I plugging in? Okay, first of all, since this one's x equals 0, I didn't copy that down, but since it's x equals 0, you're plugging in from the first line of the table. I'll show you some of the numbers, hoping that you're matching them up the same. Okay, take a look at these 3 yellow numbers. Do they line up with what you were thinking? So I took from the first line of the table the value for f, which is 1, the value for g, which is also 1, and then the value for g prime, which is 1/3. And just kind of plug them in. Everything else comes along. Same thing over here, plugging in the value for g and the value for f prime, which is 5. I'm just going to do a little arithmetic. Comes out to be 6. Yes, 6 is kind of like the final answer we're looking for. I'm more concerned, obviously, that we get some of this theory. Anything that you want to ask about there? Okay, it's a little different. It's a little different type of problem. Okay, yes, it's different. There's a name for it. I keep saying it's like numerical. There's something I'm missing here, but we can still do the problem. I guess it's kind of in theory. It's a little more of a theoretical problem. Let's see if we can do this one before we break. I'm going to skip to letter D. I told you I'm going to skip around a little bit. Again, I've seen this, and I always kind of hate these kinds of things because I know students are trying to get the right answer, but you miss that it says you're supposed to do the derivative. So you don't just plug into F and G. You know, you got to do the derivative. That's why I'm writing that down. So we have to get a new function. It was just yesterday, but do you remember? Is everything all right?
No, I think the answer to the other one is I wasn't doing something wrong. I thought it was 10, right?
It's all right. I'm glad you're asking. Careful here. I think this is usually, make sure you do the 1 squared and then multiply by 3. So what do we got here? 1 times 3 times a third. 1, 3, and a third. That's 1. That's like 1. And then plus.
Okay, never mind. Sorry.
It's all right. I'm glad you're thinking about it. Yesterday, this was called a composition. To do the derivative, you have to think about insides and outsides. This is the chain rule right here. F is on the outside. The derivative of the outside is f prime. Leave the inside alone. It's still g of x times the derivative of the inside. I like this problem because in its essence, it's the chain rule. Okay, actually, that is the formula for the chain rule. Okay, now because it said x equals 0, I need to very carefully grab my numbers from the chart at x equals 0. In other words, the first row. Okay, so I'm grabbing from the first row. I plug in the number 1. I'm going to also plug in 1/3. Extra step, f prime of 1. I got to go back to the chart. F prime of 1, I got to go back to the chart. Now I'm looking at the second row. Okay, and when I do f prime in the second row, it says negative 1/3. Okay, it was kind of designed for that to happen. Basically, that you had to use the chart twice. Something that you see. I'm going slowly on purpose because is there anything that you want to ask about? Where did we get the numbers? All right, so again, g of x from the chart is equal to 1. You just grab it. But then f prime of 1 from the chart is equal to negative 1/3. Okay, you actually have to go through both those numbers. All right. We'll do one more before when you guys get back. And then I'm kind of excited to show you that sort of that bonus problem